Okay, so this is the starting for 8.5, which is the setting for the minimum cost network flow problem. Which is abbreviated as MCNFP. Yeah, it's probably just to go ahead and say minimum cost network flow problem rather than that. Okay, so what is this thing? So this is a general rubric, or this is a general framework, you could say, for representing many network models that we've presented separately. Okay, so we're going to talk about how to do that. In particular, the transportation problem, the assignment problem, what came after the assignment problem? We had the shortest path, and finally we had the max flow. Good. So we're going to see how each of these problems can be recast in this minimum cost network. Okay, so in order to do that, let's go ahead and just try out a simple example. And so we'll need to define a few terms before we do that. So some variables and notation that we'll be using here. First off, xij will be the flow associated with the arc ij, okay, or the edge ij, or that's also the arc that moves from node I to node j, if you like. Okay, each edge will also have an associated cost for moving things along that. Will be the cost, so that's per unit flow, right? With transporting flow along arc ij. Okay, so Cij will be the cost. Good. We will also have supply nodes, and so we'll take Bi to be greater than 0. We'll represent the supply for a supply node. Bi will be less than 0 for a demand node. And finally, Bi will be equal to 0 for a transshipment node. Okay, and then lastly, we talked about conservation of flow on the nodes before, but now we have a different conservation of flow because we have these supply, demand, and transshipment nodes. We have to take that into account into our conservation of flow. And so for each node I, before we just said that outflow must be equal to inflow, but now we'll take the inflow over to the other side. We'll say that outflow minus inflow, I guess you could finish that there, is equal to Bi. Okay. Good. And so we're going to take this is basically how we're setting up our linear program, right? Okay, so let's try an example. I'll set up my network here, and then I'll come back and we'll write down the linear program for it. All right, so here's my linear program. I've got 4 nodes on this network, and I've got my, oops, let me not do everything here in red. B1 is equal to 7, so node 1 is a supply node, and it's being supplied with 7 units. Node 2 is a supply node, and it's being supplied with 5 units. And then node 3 is a demand node with minus 9 units. B4 is a demand node with minus 3 units. And the red numbers on here are going to be representing the costs, not the flow. Okay, so in this case we don't have the flow set up, and in fact the variables xij will represent how much we're going to put in each of the arcs, how much we're moving in arc ij. Okay, so let's set up our LP. Let xij be amount moved from I to j. Then we're going to try to minimize our cost, which will be 4x12 plus, let's see, I'll go in order here with ones first. So 1, 2, and then 1, 3. So that'd be 3x13. And then 2, 3 will be next. So 2x23. And then 2, 4 will be next. Plus just an x24. And then lastly, x43. 5 times x43. Good. Such that, oh, by the way, if this is my minimization problem, what's stopping me from just setting all of my xij to equal to 0? What's making me push anything through here? Yes, the outflow minus the inflow must be equal to bij. Right, so in other words, what comes out from from on this arc and from on this arc, right, has to be 7. So you can't just use zeros in here, right, and get a minimum. Okay, we'll see that as we go along. So let's see. For arc 1, 2, that flows out. So excuse me. Maybe I'll just make a note here. Note on node 1. What is the outflow? That is x12 plus x13. Okay, and so for our solution here, or our constraint, we get 1, 2 plus x13. That's it, equals 7. Okay, so then continuing, what's going to be the constraint for node 2? Incoming is 1, 2, so that's going to be negative. Then outgoing is 2, 4. And then outgoing is 2, 3. Good. And then that's equal to 5. Node 3 is next. Everything is incoming. So 1, 3. Excuse me. Okay. I shouldn't have had that peanut. Okay, let's go. Keep going. X13 is incoming. X23 is incoming. And X43 is incoming. And then that's going to be equal to minus 9. Good. And then finally, node 4. 1 incoming, 1 outgoing. So the incoming is 2, 4. And then the outgoing is 4, 3. Yeah, so that should be equal to minus 3. Good. So this is minus 9, right? Excellent. So one thing that you should notice in this, as we're going along, is that there's this pattern, plus or minus signs. Do we see why? That's because for every edge there's a starting, one of the nodes will account for the beginning of the arc, and one of the nodes will account for the ending of the arc. Okay, so every variable then will appear as a plus, um, a, a plus value and then a negative value. Okay, that's going to be important when we look at the dual. Okay, so this is going to be important in the dual. All right, but before we get to the dual, we'll finish up this problem. We're pretty much done. Um, I think the only thing here I might say is that we do want the xij to be greater than or equal to 0. And one other thing I might mention is that we're not, excuse me, yeah, I was just going to mention that the one thing that we're not accounting for in this network is like a capacity. And so we'll see how to incorporate a capacity in the general framework. So that'll be in the next video, and which will be part 2. See you there.